Welcome back to the notes. So now we're going to talk about what if we get, distinct real eigenvalues. So each eigenvalue that we find is different than the one. There's no repeated, and there's no multiplicity of solutions for eigenvalues. So if we have distinct eigenvalues of the coefficient matrix A and the homogeneous system, and let A be k sub 1, k sub 2, k sub n, which are the corresponding eigenvectors, and the general solution on the interval from negative infinity to infinity is given by x is equal to c sub 1 k sub 1 e to the lambda sub 1 t plus, and then c sub 2, our next eigenvector with the corresponding eigenvalue. We keep going until we've completed all the eigenvalues and eigenvectors that we solved for. So example 3 is find the general solution of the given system. So I want you to notice here we have linear differential equation 2. So we have a system. This, if we look at our matrix A, our coefficient matrix, that's just going to be 2, 2, 1, 3. We did this in the previous problem. Notice 2, 2, 1, 3. So because we've already solved this, when we already found the eigenvalues and eigenvectors, I'm not going to, find everything again. So we said that, we had lambda sub 1 was equal to 4, and then the corresponding, the eigenvector that corresponded to that was 1, 1. And then we also had lambda sub 2 was 1, and make sure that was 1. Yeah. And a little too far. K sub 2, the corresponding eigenvector was negative 2, 1. So therefore, when I write out my solution vector is just going to be, let me not get rid of, go through the lettering, c sub 1 eigenvector that corresponded to the eigenvalue 4, plus c sub 2 eigenvalue that corresponded to the eigenvector or eigenvalue 1. And then there's our solution. We're finished. We have found the solution to our system. So that's why eigenvalues and eigenvectors are so nice to work with, because now, hey, we found the solution to our system of differential equations. All right, now this is when I say this kind of stings, because now we're working with the 3x3 matrix. All right, working with this 3x3 matrix, we want to find the eigenvalues and eigenvectors. So again, it already gives us to it in matrix form, so all we need to do now is go ahead and write out the coefficient matrix, and you don't have to write that because we're going to do the determinant of the coefficient matrix minus the lambda I, so A minus lambda I. So what I did was I went ahead and wrote this out. If you remember from yesterday's video, if we're doing a determinant of a 3x3, just go ahead and rewrite row or column 1 and column 2 to the side, and then you can just go across. So define the first term we multiply pretty much 1 minus lambda I to the third power. So that's what I wrote right there. So that's the first value. Then what's nice about this is we do the second, and 0 times 0 times 1 is just 0. Then 1 times 0 times 0 times 0 is just 0. So that gives us the first view. Then minus, and then we're going to minus everything over to the right. So now we have to go across. So again, we're going to do the diagonal. Minus 1, minus, and then the only thing that's there is 1 minus lambda. So that's what we get right there. Multiply the next one, we have a 0, so 0, then do it again, we have another 0, so 0. So that's nice, because we can cancel out some of those zeros. Alright, now we actually go ahead and simplify this. When we do, I'm doing some math here, I just go ahead and make sure that I do 1 minus lambda cubed, and then I have the minus 1 plus lambda. Again, it's easy to make a mistake. If you forgot to distribute a minus sign, you've really messed up. So I'm not going to give you too many to do, because it takes a while to do some of these. And that's why we're only doing, 3 videos, because I want to make sure that you have time to practice these. Okay? So do the homework. All right. Now I'll simplify this, and I get minus 2 lambda plus 3 lambda squared minus lambda cubed. And I can pull out a negative lambda, so I do that, and I'm left with lambda squared minus 3 lambda plus 2. And then I factor, that quadratic right there to get lambda minus 2, lambda minus 1. Set that equal to 0, and I get my 3 solutions. So there's the 3 distinct solutions for lambda. So I found my eigenvalues. So I already know that when I write it out, it's going to be e to the 0t, which is just 1, e to the 1t, and e to the 2t. All right, now over here on the left, I actually have to, plug in. So now all I've done is I've written this in my system form. So I went straight from using my lambda, plugging it into the system. So all I did here was I just look at, when I made the determinant, I'm going to subtract 0 to all of those. So all those lambdas are just going to be 1. And so hopefully, so I just went ahead and, worked on that and did 1. And then everything else is going to stay the same. Now again, you don't have to put plus 0 k sub 2. I just did it because these are notes and I want you to see where all these values came from. And so when I plug in, I get, 1 k sub 1 plus 0 k sub 2 plus k sub 3 equals 0 for the first one, second one, and third one. When I plug in to my matrix, now I'm going to go ahead and try to solve. Now, when I look at this, and when I either add or subtract, or I can use a matrix matrices to help me manipulate this to find the solutions. I notice, oh hey, well, k sub 1 and k sub 3, if I just work on those two, they have to be the same value. Okay, well, that's great. So if those are the same value, what does k sub 2 have to be? Well, if those are going to be the same value, then hold on, let me look at this real fast. Actually, one should be different. So it should be k sub 1 is equal to negative k sub 3. So then we get that value because they are of the same sign. And because they're of the same sign, well, they have to be opposites. So we get 1, 0, negative 1. So that means that k sub 2 is going to be 0. And again, I could have made, k sub 1 be 2. If I made k sub 1 be 2, then, I would get different values. But that k sub 2 would still have to be 0. And that really came from that middle part right there. All right. Now, let's go ahead and make sure that I change my answer to. Should be negative 1. All right. Lambda sub 2 is equal to 1, so now we have 0. Okay, so we just set that again equal to the system, and now we're going to solve the system. And when we solve this one, we're going to get, well, based off of this, k sub 3 has to be 0. Based off of the middle one, you get 0 equals 0, so k sub 2 can be any value that we want it to be. And that's why I have it, k sub 2 is equal to all of our numbers. And then the last one is k sub 1 is equal to 0, so that gives me 0, 1, 0. Like, I can make that 0, 2, 0. But again, I want to keep it simple, so 0, 1, 0. All right, and then the last part, lambda, our last eigenvalue is 2, so we plug that in. We get this system, we solve. And now notice then that those two are opposites. That should be k sub 1 is equal to k sub 3. So those are going to be the same value. So k sub 1 is equal to k sub 3. That's going to give us 0. K sub 2 has to be 0 from that middle one. So we found our last solution, 1, 0, 1. Now that we have that last eigenvector, we can now plug in to our format, and we get x equals c sub 1. Now this one, actually, things have changed, so let me make this 0 and make that So we made that the first one, so that's going to be e to the 0, so that's just going to stay there. We made this one 0, 1, 0, so that's just going to change that to e to the, what's the eigenvalue? So e to the 2g. Alright, and then there you see everything is finished.